Industry skills, practical knowledge, real-world impact. This is SimpleGyan.
What industrial material can glue cardboard, harden concrete, bind foundry sand, stabilize weak soil, and even help protect a building from fire? Surprisingly, it is produced mainly from two ordinary materials, sand and soda ash. This remarkable chemical is sodium silicate, commonly known as water glass. Although it may look like a thick, colorless liquid, sodium silicate is neither an ordinary glue nor conventional glass. It is an inorganic chemical system that can flow like water, penetrate porous surfaces, and then transform into a hard, glass-like mineral bond. But how does a factory turn common silica sand into this universal industrial adhesive? Let us enter the engineering world of sodium silicate. Sodium silicate is not one single compound. It is a family of alkaline silicates represented by the general formula, Na2O.NSiO2. Here, N represents the proportion of silica relative to sodium oxide. This silica-to-soda ratio is one of the most important quality parameters. Commercial liquid grades commonly have a weight ratio between approximately 1.8 and 3.75. A lower ratio produces a more alkaline and reactive silicate, frequently used in detergents and chemical processing. A higher ratio produces a more silica-rich material suited to adhesives, binders, and coatings. Commercial water glass solutions may contain roughly 20 to 50% sodium silicate solids, with the remainder being water. Their consistency can range from a thin liquid to something resembling heavy syrup. The US EPA describes the commercial ratios and manufacturing routes, while India's MSME technical profile documents typical solution concentrations and applications. Production begins with high-purity silica sand, principally silicon dioxide, and dense soda ash, chemically known as sodium carbonate. The sand must have controlled particle size and low levels of iron, clay, and other contaminants. Excess iron can discolor the final product, while oversized particles may remain incompletely reacted. The two raw materials are weighed according to the required silica-to-soda ratio and mixed thoroughly. This dry batch is continuously fed into a gas-fired, oil-fired, or electrically heated melting furnace. Inside the furnace, temperatures typically reach between 1,200 and 1,400 degrees Celsius. At this temperature, soda ash reacts with silica, Na2, CO3 plus NSiO2 yields Na2O.NSiO2 plus CO2. The carbon dioxide escapes as gas, leaving behind molten sodium silicate glass. Maintaining furnace temperature is critical. If it is too low, unreacted sand, known as batch stones, may remain in the glass. If it is too high, energy consumption rises, refractory wear accelerates, and sodium-containing material may volatilize. The molten product is discharged as a glowing stream onto a cooling conveyor. Rapid cooling transforms it into a translucent, brittle solid called sodium silicate glass, cullet, or lump glass. Water quenching may also be used to break the hot material into smaller fragments. At this stage, the solid can be crushed and sold as granular sodium silicate, but most industrial customers require it as a liquid. The fragments therefore enter a pressure dissolver, where hot water and steam dissolve the glass at elevated temperature and pressure. The resulting solution passes through settling equipment and filters to remove insoluble sand, furnace debris, and other contaminants. Operators then adjust its concentration, density, and silica-to-soda ratio. Sodium hydroxide may be added when a more alkaline, lower ratio grade is needed. Finally, the liquid is transferred to storage tanks for dispatch in drums, tankers, or rail cars. If a dry powder is required, the filtered solution can be concentrated and spray-dried. An alternative manufacturing route reacts silica directly with sodium hydroxide in a heated pressure reactor. This hydrothermal route avoids the conventional glass melting sequence, but still requires careful control of temperature, pressure, concentration, and raw material quality. The principal furnace and dissolution process is documented in the EPA sodium silicate supply chain profile. Manufacturing sodium silicate is not simply about melting sand. The product must be engineered for a specific application. The quality control laboratory measures silica-to-soda ratio and percentage solids. They also test specific gravity or degrees Baume and viscosity. Finally, they test pH and alkalinity, clarity, color, and insoluble matter. Temperature is especially important during handling. Sodium silicate viscosity can increase significantly as temperature falls. Incorrect storage conditions may make pumping and accurate dosing difficult. Its alkaline nature also influences material selection for tanks, pumps, seals, and pipelines. Carbon steel, stainless steel, or compatible plastics are generally selected according to concentration and operating conditions. When liquid sodium silicate is applied to cardboard, wood, mineral fiber, or another porous surface, it penetrates the microscopic pores. As water is absorbed or evaporates, the silicate becomes increasingly concentrated. Carbon dioxide, acids, or polyvalent metal ions can further trigger the formation of a rigid silica-rich network. In simple words, the liquid mineral gradually turns back into a glass-like solid. This gives sodium silicate several important advantages: strong initial tack, resistance to high temperature, low odor, low organic solvent content, and good compatibility with mineral surfaces. That is why it is widely used in corrugated cardboard, paper tubes, fiber drums, and industrial packaging. In foundries, sodium silicate binds sand particles together. Passing carbon dioxide through the prepared mold converts the liquid binder into a hardened silica gel, rapidly producing a strong mold or core. It is also used in welding electrodes, refractory mortars, abrasive wheels, concrete treatments, soil stabilization, and drilling operations. In water treatment, it can assist corrosion control, coagulation, and stabilization of iron and manganese. The EPA lists cardboard, detergents, adhesives, soil stabilization, concrete, and water treatment among its major uses. Most organic adhesives contain carbon-rich material that can burn or produce smoke. Sodium silicate is different. It is an inorganic mineral binder and does not act as fuel. When exposed to heat, water within the silicate absorbs energy as it evaporates. The remaining material forms a rigid mineral barrier that helps separate the underlying surface from heat, flame, and oxygen. Sodium silicate is commonly combined with vermiculite, perlite, mineral fibers, clay, or refractory powders to manufacture fire-resistant boards, doors, insulation, coatings, cements, and sealing compounds. However, sodium silicate alone does not automatically make a structure fireproof. The thickness, fillers, adhesion, moisture resistance, and complete tested assembly determine the actual fire resistance rating. Its limitations include brittleness, shrinkage, and sensitivity to prolonged water exposure. Engineers therefore modify formulations with fillers, polymers, or other silicates to improve flexibility and durability. Despite its glass-like appearance, concentrated sodium silicate is strongly alkaline. Depending on its ratio and concentration, it can cause serious eye damage, skin irritation, or chemical burns. Operators require goggles or face shields, chemical-resistant gloves, protective clothing, and controlled spraying. Dust control is essential while handling silica sand and powdered products. A 2025 USDA technical assessment summarizes the concentration-dependent skin, eye, and respiratory hazards. Environmentally, water-based sodium silicate can replace some solvent-containing organic binders, but its production is energy-intensive, and the soda-ash reaction releases carbon dioxide. Modern plants therefore focus on efficient furnaces, improved insulation, heat recovery, and low-carbon electricity. So, the answer to our opening question is astonishingly simple. Sand can become an industrial liquid, one that glues, seals, hardens, and protects against fire. Sodium silicate may be nearly invisible in the finished product, but behind countless cartons, castings, refractory linings, concrete floors, and fire-resistant structures lies the extraordinary engineering of water glass.